This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section of the lecture material, I'm going to be discussing containers, iterators, and algorithms. A large part of the C++ standard library is actually a collection of class and function templates that are collectively known as the Standard Template Library, or STL. The STL is comprised of three basic building blocks: containers, iterators, and algorithms. Containers essentially store elements for processing. An example of a container is the vector class template. Iterators allow access to elements for processing, and these elements are often in containers, but they don't necessarily have to be. So iterators essentially provide access to data for processing. And then lastly, algorithms perform the actual processing, for example, searching or sorting or other types of algorithms. A container is a class that represents a collection or sequence of elements. And usually container classes are class templates. And there are two different flavors of containers. The first is what's known as a sequence container. A sequence container is a collection in which every element has a certain position that depends on the time and place of insertion of the element. Some examples of sequence containers include the array class template, which corresponds to a fixed size array, the vector class template, which corresponds to a dynamically sized array, and the list class template, which corresponds to a doubly linked list. Another flavor of a container is what's known as an associative container, and this is a collection in which the position of an element in the container depends on its value or some associated key and some predefined sorting or hashing criteria. Some examples of associative containers include set, which is essentially a collection of unique keys that are sorted by key. Another example is map, which is a collection of key value pairs that are sorted by key where the keys are unique. On this slide, I've listed some sequence containers from the standard library, along with some associated container adapters. So first I'll start with the sequence containers. The first of these is array. This represents a fixed size array. A vector, which represents a dynamically sized array. DQ, which stands for double-ended queue. It's a queue that you can essentially add and remove elements at the beginning and end. Forward list, which is essentially a singly linked list. And list, which is essentially a doubly linked list. Then we have what are called container adapters. A container adapter provides some special behavior on top of a sequence container. For example, a stack container adapter could be used to provide a stack interface to a vector container. So we have three different container adapters. The first is a stack, which essentially provides a stack interface to a container. Queue, which provides a FIFO queue, first in, first out queue, interface to a container. And priority queue, which provides a priority queue interface to a container. On this slide, I've listed some of the associative containers in the standard library. And the associative containers can be partitioned into two groups, what are called ordered containers and what are called unordered containers. So I'll start with the ordered containers first. The first of these is called set, which is a class template. Basically, all of these are class templates. And what a set is, the individual elements of a set are keys, and they have to be unique. And the elements in the container are sorted by key. Then we have what's called a map. In the case of a map, the individual elements are pairs of a key and a value, which go together. The elements are sorted by key, and the keys have to be unique. Multiset and multimap are very similar to set and map. The only difference is that duplicate keys are allowed in the case of multiset and multimap, whereas in the case of set and map, the keys have to be unique. Then we have the unordered containers. The first of these is unordered set, and this provides a collection of unique keys which are hashed by key. They're not sorted, but instead they're hashed. Basically, these are like hash tables, these types. Unordered map, it provides a collection of key value pairs, so the individual elements are a key plus a value, and the elements are hashed by key, and the keys have to be unique. The only difference between unordered set, unordered map, and unordered multiset and unordered multimap are these last two container types, unordered multiset and unordered multimap, allow for duplicate keys. For the most part, the container classes in the standard library tend to share a fairly similar interface, In other words, they have similarly named member functions with similar types of parameters, similar types of return values, similar types of semantics, and so on, to whatever extent makes sense. And what I have listed on this slide are just some of the typical container member functions that you can expect. So the containers typically will have a default constructor, which will create a container that contains no elements. We have a copy constructor, a move constructor, so we can copy and move containers. A destructor, of course. We have an empty member function to test if the container is empty, size member function that gets the number of elements in the container, pushback that inserts an element at the end of the container, clear which removes all the elements from the container, and then of course an assignment operation, also subscripting operators to access elements in the container. And there's other member functions as well, but this gives you a feeling for some of the typical member functions that containers have. On this slide, I have a code example that makes use of a container class from the standard library. In particular, this example makes use of the vector class template. So let's look at the example in more detail. You notice near the beginning I include the header file vector. This header file has all of the declarations and definitions necessary for the vector class template. Then in the main function, I create a vector of ints called values. The parameter to the vector class here, the first parameter, specifies the type of the elements in the vector. So this vector has for each of its elements a value of type int. And also this object is default constructed. So this, for a container, a default constructor will create an empty container. In other words, a container with no elements. So values is a vector with no elements initially. Then in the loop below, we're going to loop for I going from 0 up to and including 9. And the looping variable I, we're going to call pushback for it. So we're going to push back the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 into the vector values. So this is going to append to the end of the vector each of these values in succession, which will result in the vector values having the elements 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 when the loop completes. Then in the next loop below, we're going to print out each of the elements in the vector by using the subscripting operator. So we're going to loop for I going from 0, the first index into the array, up to but not including size, which would be the last element in the array, or the last index. And we print out values of I. So we're using the subscripting operator to print out the corresponding element. And then we print a new line here. And the program is going to output 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Before introducing iterators in any detail, I would first like to discuss the motivation behind iterators. So consider an implementation of an algorithm such as sorting. In order to perform its task, the algorithm must be able to access the data to which the algorithm is being applied. There are, however, many different ways in which this data could be organized in memory. For example, the data might correspond to elements in a container, and each type of container has its own distinct way of organizing its data in memory. For example, on this slide I have some diagrams illustrating how data is laid out in the case of an array and a vector, and how things are laid out in the case of a doubly linked list. In other words, the list container class in the standard library. And you can see these layouts are very different. In the case of a vector or array layout, all the elements are contiguous in memory. So element 1 comes immediately after element 0. Element 2 comes immediately after element 1, and there's no extra data. The only data that's stored here is just the element data itself. In the case of a list container, which is essentially a doubly linked list, each element corresponds to a node in the list, and each node in the list has not just the actual data element itself, but has a pointer to the next element in the list and a pointer to the previous element in the list. And these pointers are necessary because in the case of a list, the nodes are scattered all over memory. They're not necessarily contiguous. Therefore, pointers are needed to tell you where the next and previous elements are. So when a different memory organization is used for data, the processing steps required to access the data must also necessarily change. Having the manner in which the data is accessed depend on its layout in memory is extremely undesirable because this forces the code for the algorithm itself to be directly responsible for understanding and handling all of the possible data layouts. In turn, this makes writing a single generic algorithm that works for all possible data layouts impractical. Consequently, in order to facilitate the development of generic algorithms, we need a single uniform interface for accessing data that is independent of how the data is organized in memory. And such an interface is exactly what iterators provide. To further illustrate the need for a single uniform interface for accessing data in algorithms, let's consider an example. And the example I'd like to consider is a generic algorithm which sets all the elements in a container to 0. So let's consider the specific case of an array or vector of int elements, as what I've shown here. And basically our goal here is we want to initialize all the elements in the vector to 0. We could use code which looks something like this. Because the particular elements in the vector are all ints, we could use pointer to ints. So we could use a pointer to int which is initialized to the very beginning of the array to begin with. In other words, this begin here denotes a pointer to the first element in the array, and n denotes a pointer to one past the last element. So we could use code which looks something like this. We initialize our pointer to be the beginning of the array. We loop as long as the iterator is not equal to end. In other words, it's one past the last element. Each time through, we increment the pointer to point to the next successive element. And each time through the loop, what we're going to do is we're going to dereference that pointer and set the value that it refers to 0. So after this loop runs, all of the elements in this array would be set to 0. But let's say we want to turn this into a generic algorithm. And we want this to work, for example, even if the container that we're dealing with is a doubly linked list. In the case of a doubly linked list, the data is laid out very differently from what we have here. But we'd really like to be able to write similar code which looks like what's shown here and have it works in the case of a doubly linked list and in the case of every other type of layout that we might want for our data. Well, it turns out that we could do this, and the trick that we can use is instead of using a pointer to int as the type that we're using to access the data, what we'll do is we'll create a user-defined type which looks a bit like a pointer in the sense that it provides all the operations that we need here. We can initialize it to some value, we can compare it to another value, we can increment it, we can also dereference it. But what will be different is that we're not going to use a built-in type. This user-defined type will provide all of these operations, and it will do the correct thing for whatever memory layout is used for the particular data that we're accessing. So in the case of an array or a vector, these operations would do one thing. In the case of a doubly linked list, they would do something different. In the case of some other type of container, they would do something yet different again. But the idea is, no matter how we're laying the data out in memory, the algorithm that we're writing still accesses the data in the same way. It's basically using operations which look like pointer operations, dereferencing, incrementing, decrementing, comparing to things that look like pointers. But in fact, they're not pointers, there's some user-defined type. And this user-defined type is what's called an iterator. At this point, I can now introduce the notion of an iterator. So an iterator is simply an object that allows iteration over a collection of elements where the elements are often, but not necessarily, stored in a container. Iterators support many of the same operations as pointers. In fact, a pointer is an example of an iterator. But more frequently, iterators tend to be user-defined types. The reason why is that when the data is laid out in memory in a more complex manner, pointers aren't sufficiently sophisticated to be able to handle iteration over data with a more complex data layout. In this case, a user-defined type is needed. Iterators have 5 different categories in which they can be classified. And different categories have different levels of functionality. And I've listed the different categories from the least level of functionality to the most level of functionality. So at the least end of things, we have input iterators, and then this is followed by output iterators, forward iterators, bidirectional iterators, and random access iterators, which have the most functionality. Depending on which kinds of iterators we're using, there's certain possibilities in terms of how we're allowed to access the data. For some kinds of iterators, we can only access data in the forward direction. In other words, we can't iterate over the data backwards. Some iterators, we can access the data both in the forward and backward direction. And some iterators allow access in any order, in other words, complete random access data. There's also some possibilities in terms of whether we're allowed to read or write the data that's being referenced by the iterator. In some cases, we can only read the referenced element, and in some cases, it may only be once that we're allowed to do this, or we're allowed to do multiple times. In some cases, we may only be allowed to write the referenced element, in other words, we can't read it. And in some cases, we can only write it once, or we can write it multiple times. And then lastly, we might be able to both read and write the referenced element. And we might be able to do this once, or we might be able to do this multiple times, depending on the particular flavor of iterator we're using. And then lastly, iterators come in both const and mutable forms. By mutable, I mean non-const. A const iterator is an iterator that cannot be used to modify the thing that the iterator refers to. In other words, it's like a pointer to const. A mutable iterator or non-const iterator is an iterator where we're allowed to modify the thing that the iterator refers to. In other words, it's like a pointer to something that's non-const. On this slide, I have summarized the abilities of iterators from each of the various iterator categories, and also given examples of types that provide iterators from each category. So let's walk through each of these categories one at a time. So the first category is an input iterator. An input iterator can only be used to read data, and in particular, it can only read data once. In other words, you can only dereference an input iterator once, and you can only access data in the forward direction. An example of a class that provides this is iStream iterator. It's an iterator that allows you to read from a stream, from an iStream, using an iterator type interface. The next category is output iterators. Output iterators can only be used to write data, and you can only write the data once. In other words, you can only dereference the iterator once, and you can only access the data in the forward direction. An example of an output iterator is the OStream iterator, which allows you to write to an OStream, to an output stream, using an iterator type interface. The next category is a forward iterator. It can be used to both read and write data, but it can only be used to access the data in the forward direction. And some examples of classes that provide this are forward list, unordered set, unordered multiset, unordered map, and unordered multimap. The next category is bidirectional iterators. With bidirectional iterators, you can both read and write data in both the forward and backward direction. Some classes that provide this type of iterator are list, set, multiset, map, and multimap. And then lastly, we have the random access category of iterators. It can be used to both read and write data with random access. In other words, you can access the data in any order you like. Some examples of types that provide random access iterators are any built-in array type in the language, so any type of array. Also the array class in the standard library, as well as the vector class, double-ended queue class, and the string class. This slide summarizes the operations that are provided by an input iterator. With an input iterator, you can copy construct it. You can dereference it as an R value. In other words, you can dereference it in a context where you're reading the value that the iterator refers to. You can't write to it, however. And also, equally importantly, you can only dereference the value once. In other words, you can only read the value once that the iterator refers to. It also provides the prefix and postfix increment operations, which step forward to the next element in the sequence that you're iterating over. You can test input iterators for equality, and you can test them for inequality. They're not assignable, however. You can't assign one input iterator to another. This slide summarizes the operations that are provided by output iterators. First of all, output iterators are copy constructible. They can be dereferenced as an L value. In other words, the dereference operator can be used in contexts where you're writing to the element that the iterator refers to, as opposed to reading. It can't be used for reading, but it can be used for writing. Furthermore, another important constraint is that you can only dereference a particular element once. Output iterators also provide the prefix increment and postfix increment operations, which step forward to the next element in the sequence. Output iterators are not assignable, so you can't assign one output iterator to another, and they don't provide any comparison operations, so you can't check to see if two output iterators are equal or not equal. This slide summarizes the operations that are provided by forward iterators. With forward iterators, we can default construct them, copy construct them, assign them. We can dereference them, and unlike the case of input and output iterators, we can dereference them as many times as we like, so forward iterators can be used in multipass algorithms. The prefix increment and postfix increment operations are provided, which step forward to the next element in the sequence being iterated over. We can test forward iterators for equality, we can test them for inequality. When we're dereferencing a forward iterator, though, we have to make sure that it's actually valid to dereference the iterator. In other words, the iterator actually has to refer to valid data before we try to dereference it. This slide summarizes the operations provided by bidirectional iterators. Essentially, bidirectional iterators provide all the operations that forward iterators do, but in addition, they also provide the prefix and postfix decrement operations, which allow you to step backwards in the sequence that's being iterated over. This slide summarizes the operations provided by random access iterators. Random access iterators provide all the functionality offered by bidirectional iterators, as well as some additional operations that allow random access to elements. So for example, if we have an iterator A, we can apply the subscripting operator where n is an integral value. And what this will do is it will dereference the element at index n relative to A in iteration order. And n, by the way, can be negative, in which case this will dereference an element which precedes A in iteration order. We can apply the plus equals operator, and what this will do to the iterator A is it will step it forward n elements in iteration order. We can apply the minus equal operator to an iterator A, in which case this is going to step n elements backwards in iteration order. If we say A plus n, this will give us an iterator which refers to the nth next element after A, and n plus A is basically the same as A plus n. A minus n allows us to obtain an iterator which is for the nth previous element relative to A in iteration order. A minus b, if we take the difference between two iterators, A and B, this gives us the number of elements that separate A and B. A less than b tests if A comes before B in iteration order. A greater than b tests if A comes after B in iteration order. A less than equal to b tests if A is not after B in iteration order. And A greater or equal to b tests if A is not before B in iteration order. And by the way, pointers are examples of random access iterators. And perhaps they're maybe the most common example of random access iterators that are used in programs. On this slide, I have a code example illustrating the use of iterators. And in particular, this is done in the context of the vector class template. So if we look at the main function, to begin with, we create a vector of ints called values. We're passing a single parameter to the constructor, the value 10. So this is going to correspond to the number of elements in the vector. So we're going to be creating a vector with 10 elements. On the next line, we want to print out the number of elements in the vector, but rather than use the size member function to do this, we're going to get some additional practice with iterators, and we're going to perform the calculation of the size of the vector by using iterators. So what we're going to do is we're going to get an iterator which refers to the end of the vector, which is 1 past the last element, and we get an iterator which refers to the first element in the vector, which is begin. And then we take the difference between these. And remember, the difference between two iterators is the number of elements that separate them. But the number of elements that separate begin and end is going to be the number of elements in the vector. So this is the same as the size. So we're going to effectively print out the number of elements in the vector, or the size of the vector. The next loop here, what we're going to do is we're going to initialize the elements of the vector to have the values 0, 1, 2, 3, 4 up to 9. So we create an iterator variable called I, and we're going to loop while I is going from begin to end. And each time through the loop, we're going to increment the iterator I. Inside the loop, what we do is we initialize the element that I refers to, in other words, star I, to I minus values.begin. The first time through the loop, I is equal to values.begin. In other words, I is the begin iterator for the vector. So when we take the difference between these two elements, because they refer to the same element, they're the same iterator, the difference between them is 0. In other words, the number of elements that separate these two iterators is 0 in the iteration order. So the first time through the loop, we'll initialize star I to 0. The second time through the loop, I will have been incremented once. So when we take the difference between I and values begin, there will be one element that separates these two values in the iteration order. In other words, the iterator I and the iterator begin. So the second time through the loop, the I minus values begin will be equal to 1. And then the next time through the loop, it will be equal to 2, and then 3, and then 4, and so on up to 9 in the last iteration. And each time we're assigning the value to star I. So in effect, as this loop iterates and runs, what it's going to do is initialize the elements of the vector to have the values 0, 1, 2, 3, 4 up till 9. Then in the last loop, we print the elements of the vector. So to do this, we use a const iterator, because inside the loop, we're not going to use the iterator to change the element that the iterator refers to, so we can use a const iterator as opposed to just an iterator. Our iterator is called I. We initialize it to cBegin, and we loop until it becomes equal to cEnd, and each time through the loop, we increment the iterator. And then inside the loop, all we're doing is we're just dereferencing the iterator to get the value that it refers to and printing that value out. At this point, I want to make a few brief comments about common problems that can arise when using iterators. By far, one of the most common problems is dereferencing an iterator that doesn't validly reference any object. So be very careful. Anytime you use a dereferencing operator on an iterator, be sure that it actually refers to some valid object. Some operations on containers can invalidate some or all of the iterators referencing elements in the container. So for this reason, it's critically important to know which operations invalidate iterators in order to avoid accidentally using an iterator that has been invalidated. A few other comments about iterators: incrementing an iterator past the end of the container or decrementing an iterator before the beginning of a container results in undefined behavior, so be careful not to do this. And then lastly, when you're using input and output iterators, be very careful to only dereference the iterator once at each position. At this point, I'd like to talk about algorithms in the standard library. So an algorithm is a sequence of computations applied to some generic type. So in other words, an algorithm in the context of the standard library is typically some sort of template code, for example, a function template. And the algorithms use iterators to access the data that's involved in computation. The reason for this is the algorithm has to be able to work regardless of how you've chosen to lay out the data in memory. Therefore, the algorithm needs to have some kind of uniform way to access the data regardless of how it's laid out in memory. And the mechanism that uses to achieve this is iterators. Essentially, iterators provide a uniform interface for accessing data regardless of how the data happens to be laid out in memory. So as long as you can provide an iterator that can provide access to the data for the way you've chosen to lay it out in memory, you can use the algorithms from the standard library. And typically, a pair of iterators will be used for various algorithms in order to specify a range of elements on which to perform some computation. So for example, you might want to sort some elements. So you provide two iterators, one to indicate the start of a range of elements, one to indicate the end of the range of elements, and then you pass these into, for example, a sorting function, and then it will sort all of the elements in that range. In what follows, I'm only going to provide a brief summary of the algorithms in the standard library. There's quite a few of them, and you could devote a lot of time to discussing them. For details beyond what I'm going to cover here, you can refer to the two links that are given at the bottom of this slide. On this slide and the next several slides, I have a summary of some of the algorithms provided by the standard library. I'm not going to go through all of them in detail because you'll probably forget them as fast as I go through them. And even if you want to use them, you'll probably want to look up more detailed information on them anyway. But I'll just point out a few functions here and there, what they do, and just so you have some idea of some of the types of functionality that are provided. So for example, the for each function can be used to apply a function to each element in a range. The equal function can be used to test whether the elements in two different ranges are the same or different. This slide lists some more functions in the standard library, and I'll just highlight a few of them. Copy can be used to copy a range of elements, and then there's some variations on copy. Copy if copies elements only if a certain condition is satisfied by the element. Copy n is used to copy n elements, where n is specified as a parameter. Move is used to move a range of elements. And move backwards is used to move a range of elements, but moving them in the backwards order. This might be necessary to use when the source and destination locations overlap with one another. Swap is used to exchange the values of two elements, and there's a bunch of other functions listed on this slide, but again, I'm not going to go through all of the functions in detail. On this slide, the list of functions or algorithms in the standard library is continued, and I'll just go through a few of the functions in detail, in particular the ones that are highlighted in magenta. So fill can be used to fill a range with a value. This is quite useful for initialization, often in code. Reverse can be used to reverse the order of elements in a range. Shuffle can be used to randomly permute the elements in a range. Again, this slide continues with our list of algorithms or functions in the standard library. The standard library provides some functions for partitioning, also for sorting as well. In the sorting category, there's a function called isSorted, which tests if a range is in sorted order. IsSortedUntil finds the first element that's not in sorted order in a range. Sort can be used to sort the elements in a range. And maybe I'll also mention stable sort also performs a sorting operation for a range, but it preserves the order of equivalent elements. So if you have two elements that are deemed equal with whatever sorting criteria that you're using, a stable sort will guarantee that after the elements have been sorted, the elements that are considered to be equal will have the same relative order that they had before they were sorted. Again, on this slide, we're continuing with our list of functions or algorithms in the standard library. There's some functions for doing binary search operations, such as binary search, which checks if a value exists in a sorted range. There's set operations, like merging and set union, intersection, set difference, and so on. The standard library also provides a number of different functions for maintaining heaps. Heaps are useful in a lot of different types of algorithms. The standard library also has some algorithms or functions which relate to minimum and maximum values. So for example, the min, max, and min max functions return the minimum, maximum, and maximum of some given values. Min element, max element, and min max element get the smallest, largest, and smallest and largest elements in a range. The standard library also provides some algorithms or functions that can be used for numeric operations. The first that I have listed here is iota, which can be used to fill a range with successive values. So for example, if you wanted to fill a range of ints with the values 1, 2, 3, 4, 5, 6, 7, 8 or something like this, successive values, iota could be used to accomplish this. Accumulate can be used to sum the values in a range. Inner product can be used to compute inner products involving elements in a range. And there's a few other functions here which relate to numeric computations as well. On this slide, I have a code example that makes use of a few of the algorithms from the standard library, namely the count, shuffle, and sort algorithms. So let's look at this code example in more detail. To begin with, you'll notice that I include the header file algorithm. This is necessary to pick up any definitions or declarations that relate to algorithms that I'm using in this program. You'll also notice that I've included the header file random. This is necessary because, as it turns out, later I'm going to be using some of the random number generator functionality from the standard library, for which this header file is necessary. And if we look at the main function for this program, I create a vector of ints called values, which is default constructed, so values initially has no elements in it. Then I create an int variable x, and I'm going to loop reading from standard input into x. And each value that I read into x, I'm going to use pushback to add it to the vector values. So after this loop finishes, I'll have added a number of elements to the vector values. And then what I want to do next is I want to print out the number of elements in the vector values, which is equal to 0. So to do this, I'm going to use the count algorithm. And the count algorithm takes 3 parameters. The first 2 parameters are iterators that provide a range over which you're going to count elements. And then the last parameter is the value that you want to count. So how many elements are equal to the value 0, for example. So because I'm iterating over all of the elements in the container, because I'm specifying begin as the starting point, end as the end, the range I'm specifying is all the elements in the vector values. This is going to count the total number of elements which are equal to 0. And the return value of count is just the number of elements that were counted, and then I print this out. In the next step, what I'm going to do is I'm going to randomly permute the elements of the vector and then print them out again. So I create a random number generation engine, which I've called engine here, and then I invoke the shuffle algorithm from the standard library. It takes 3 parameters, at least in the way that I'm using it. The first 2 parameters specify a range of elements to be shuffled. So because I'm specifying begin and end, I'm going to shuffle all of the elements in the vector values. And then the last parameter here is just a random number generating engine that's used to do the permutation. So the shuffle function will shuffle the elements. Then I'm going to print out the shuffled elements. So I loop over all the elements in the vector values by using a range-based for loop, and I print out each of the elements. Then lastly, I'm going to sort all of the elements. So I'm going to use the sort algorithm from the standard library. In the way that I'm using it here, it takes 2 parameters, which specify a range of elements to be sorted. Because I'm specifying begin and end, it's going to specify the entire contents of the vector values to be sorted. So this will perform a sorting operation, and then after the sort operation completes, I print out the sorted elements. So I'm using a range-based for loop here to loop over each of the elements in the vector values, and I print out each of these elements. When using algorithms in the standard library, it turns out that functors are extremely useful. So I'd like to go through an example of using a functor in conjunction with some of the algorithms from the standard library. But before I do this, I first need to introduce one particular algorithm from the standard library in a little bit more detail. And in particular, the algorithm is known as transform. This is a function template in the standard library. And what this transform algorithm does, it takes as input parameters 2 iterators which specify a range, first and last. They specify a range of input data to iterate over. It takes another iterator which refers to a place to write the output data that's generated by this transform operation. And it also takes something called OP, which corresponds to a function or functor that can be invoked with the function call operator. And what this function will do is for each element in the range from first to last, it will apply this op function to that element, and then the return value from the op function is then written to the place indicated by the iterator result. So first and last are basically corresponding to a range, which is your input data, and then result is an iterator which corresponds to the place to write the output. And by the way, these can overlap. So you could, for example, choose result to be equal to first, in which case you would overwrite the data that you started out with the new values that you've computed. And the code for the transform function might look like what's shown here. It's a very simple function. Basically, you loop. Well, first is not equal to last. You're going to loop over each of the elements. And for each element, what you're going to do, you're going to take the current element, which is represented by first here, dereference it, and pass this into the function op, or functor. Then this is going to return a value, which is then written to the result, where the iterator result refers to. And then we increment first, increment result, and we keep looping until we've iterated over all the data. So OP is just any entity that can be used with the function called syntax. In other words, it can be either a function or a functor. But as it turns out, functors tend to be much more useful in conjunction with generic algorithms. On this slide, I have a code example that makes use of a functor in conjunction with one of the standard library algorithms, in particular the transform algorithm. And basically what I have a vector of doubles called V, which is initialized to 1, 2, 3. And what I want to do is I want to use the transform algorithm from the standard library to double each of these elements. So after everything is said and done, I want, instead of having the values 1, 2, 3 stored in the vector, I want the values 2, 4, and 6. In other words, the original value is doubled. So what I do is I use the transform algorithm, and I specify for the input range of the data that I want to operate on begin and end for V. So this is going to be all of the elements in V, in other words, 1, 2, 3. I specify for the destination where to write the result to be begin for V. So in other words, I'm going to overwrite the contents of this vector with the values that I compute by using the transform algorithm. And then the most critical thing is the last parameter to transform. This is a functor. And if we look up above to see how this is defined, MB, this functor or function object, has type multiply by. And when we constructed this object, we passed a parameter of 2 into the constructor. So let's look above and see what this is doing. So multiply by is this type here. So when we construct the object with this constructor, we're passing in a value of 2 for factor. So what the constructor is going to do, it's going to take this value of 2 for factor and store it into the data member called factor underscore. So in other words, this data member here is now going to have the value 2.0 stored in it. Then later on, when we invoke the transform function, it's going to, for each element in the range from begin to end here, it's going to invoke this functor. In other words, it's going to invoke the function call operator for it. So the first time through the loop inside this transform function, it's going to invoke MB for the first element in our range from begin to end, which is going to be this element here. So 1 will get passed in as x. Then it takes x, it multiplies it by factor underscore, which is 2, because when we created this object, we initialized this value to 2. So it'll compute 2 times 1, which is just doubling the element that was passed in here, and it returns the doubled value. And then this value is then written to where begin is specifying, which is just going to be the first element in the array. So it's going to basically read this element, double it, and then write the doubled value over top of the value that was there originally. And then as the loop inside transform iterates, it's going to proceed on to the next element. The functor will get invoked with the value 2, which gets doubled and then rewritten with the value 4. And then in the last iteration inside of the transform function, it will read the value 3. Then it gets invoked. Function call operator then gets invoked with the value 3. It gets multiplied by factor underscore, which is equal to 2, which doubles the value, which returns 6. And then 6 is overwritten with this value here. So this has the effect of doubling each of these elements in this vector. And then the last line here is just printing out all the elements in the vector to confirm that in fact they have the values 2, 4, 6.